so she beat me to the punch on that one. And so, it seems like, the technology became available, and we're seeing, people taking advantage of it. And I wouldn't be surprised if we started seeing this stuff in the wild as these chips became, more deployed. In about a year or two, most likely, there'll be active stuff taking advantage of this. And so what does a hardware VM rootkit do? What it does is first, you have to get into the kernel. I mean, in case everyone's not really clear on how kernel rootkits and modern rootkits work, you have to have root first, and then you can actually use these to maintain access. So choose your favorite way to get root, get into ring 0. Once you're there, it carves out some memory for its hypervisor, and it basically shares, or at least my design sort of shares the address space with the operating system. And then what we're going to do is basically take the running operating system and create a VM that is initialized to the state of the running operating system. And basically this just allows us to migrate it right into the VM. And once we have it running, what we're going to do is we configure the VM to notify us when there's interesting device access. And we're just intercept access to interesting hardware. And this can be disk, network card, things like this, and use that to implement our rootkit features. We can also respond to magic instruction sequences, and use those as a command and control channel or backdoor. Basically, how I implemented this is it's a loadable kernel extension that basically just you load it up, installs the rootkit, and then unloads itself and lets it keep going. And it's not a lot of code. It's maybe a few thousand lines, if even that. And it's 3 main areas. We have VMX init, initializes the VMX state of the processor, detects the capabilities, gets everything set up, and then the real magic is in the sauce in VMX fork. Basically, that's where it takes the running state of the operating system, initializes the VM with it, and basically conceptually splits the the entire system into running the guest OS and the hypervisor in two different lines of control, when it's running the VM or when it's running the hypervisor. And one of the nice things about this is because my hypervisor is sort of parasitic in that it lives in the same address space, I can use kernel services. I can call functions in the kernel. I can basically do a lot of other stuff in there, as long as I don't as long as it's reentrant. It's the same reason why you don't use a lot of functions that use the heap from signal handlers, because basically a signal can get delivered at any time in the execution of your program. Heap can be left in an inconsistent state. Various other functions can be in an inconsistent state. If you call any of those functions from a signal handler, you have problems, and your send mail. Basically, the same reason here, the VM can exit at any point in time. In between, it's updating the kernel heap. You have no clue what state that's in. And when you're in the hypervisor, if you use something that depends on state that may be left in an inconsistent way by the guest, you get a nice kernel panic. And nothing says rootkit stealth like a kernel panic. And basically, we have our event handler on VM exit. So whenever the VM exits, we need to figure out what the event was and handle it. And this is the most complex diagram I have ever made in my entire life. I am serious. I spent way too long on this. And hopefully it's worth it. Hopefully it illustrates the mental gymnastics required to understand what's going on here. So we don't have a mouse. Basically, on the left, we have the operating system is running, and we have the kernel extension is loaded, and VMX fork is running, and then basically, the little X means what used to be the original OS is now dead. And we do a VM entry, and the OS, the guest OS, continues executing in the VM until a VM exit happens, and it goes back to the hypervisor, which is occupying basically the same address space as the kernel, or as the guest OS, but I just have my memory carved out that is kept separate. it goes to on VM exit, handles its thing, then it resumes the guest. The OS continues and back and forth. Give a little details. Oh, giving a little details, but I'm also not releasing my code. So if you want to, write your own like this, take notes, check my slides, or just do what I did and crib a lot of source from Zen. So basically, initializing, VMX, you just have to, check for the feature in CPU ID. You have to enable it. One of the nice features of Intel VTX is hardware manufacturers can actually lock, in the BIOS, can lock virtual machine extensions. They can turn it off. So basically, like I think the Intel Mac Minis, this was accidentally done. There was some bug where they were locked in the BIOS and you had to have a EFI patch to actually enable it so you could run parallels. But that's one thing you can do to prevent these things is if I don't need to use anything virtualization, you can just disable it in the BIOS, be done with it. But so when I'm going through this, initializing it, I have to enable it, allocate some physical memory for the VMCS page, enable VMX operation for the current processor, and that actually brings up a good point that VMX operation and state is per processor. And so there was kind of a fun thing of development was, I'm on a Core Duo, and basically my kernel thread kept migrating between processors in the middle, and that was awesome. So what I did is I just turned one off. It's called cheating for a demo and a prototype. But basically, when you're developing like production systems like this, like Zen has to do a lot of work to basically make sure that they're on the same processor and keep the state separate between processors. It's an added caveat. So when you're actually forking the system, basically you need to create the memory for the hypervisor, carve out code, stack, and data space for it, and just initialize the VM state to that of the running operating system. And then basically figure out the execution controls you want to do to minimize VM exits. And so what I do for a rootkit, basically how we do this is we say, we don't really care about guest exceptions. We'll let the OS handle them. If it doesn't handle them, it'll crash just like it normally does. And we'll just basically set a VM exit or configure a VM exit for I/O access that we're interested in. And then we just, for Intel, you need to basically set the instruction pointer and stack pointer for where the guest resumes and where the host resumes. And basically, then you say, OK, just launch. And basically, you have now forked into those two locations, the instruction pointers that you gave it for the guest and for the host. And basically, on the VM exit, jumps to the instruction pointer that you configured. And you basically handle the event in what I called on VM exit. And some of the things you have to do here are, there are certain instructions and certain actions that always cause a VM exit that you can't ignore. One of them is the instruction CPU ID. Basically, you can use this to present a virtualized CPU to the guest that is it's like a Pentium 3 or just doesn't have a lot of the VMX features, so they don't know they're available and can't use them. Basically, operating system registers like CR0 and CR4. Obviously, you want to control the page table and the VMM system or the memory mapping that the guest OS uses. Machine status registers, you want to be able to operate those and let the guest see some, modify some. And basically, this is where you implement the backdoor functionality. And basically, how I did it is basically use the CPU ID instruction as a command channel. I did that because CPU ID is unprivileged. You can execute it as a normal user. And it always causes a VM exit. So it always passes control back to my hypervisor. It can see what's going on and take action. And this is where you'd also basically look at device access, filter it, do things like, whenever there's a request to the disk, you look at the ATAPI packet, look at the blocks in it, and you have a list of, you use the CPU ID instruction to add, disk blocks to the hide list. And basically from there, it'll just, filter all the ATAPI packets. If a request goes in for a hidden block, it'll just, make sure that it gets a null block. Do the same thing for, at least on the MacBooks for USB to record keystrokes, do all this stuff. CPU ID command channel is pretty simple. reason I did it, it always causes a VM exit, can be executed unprivileged. And what I did is just a magic value in EAX indicates a requested action, and do stuff like if EAX equals dead and something else, or is hex dead and something else, basically the rest of that is the PID that you want to change to root. Or you can say, hide this process, and so on. And actually, this is what I'll demo in a couple minutes here. Several challenges in implementing this. Like I said, VMX operation is per CPU. Keeping my kernel thread when I'm initializing things on one CPU is a pain in the butt. I couldn't find the kernel call to say lock me to this thread, so I'd have to bounce back and forth. I'm not implementing a production system here. I'm just playing with things, so I didn't really care. Also migrating one CPU of an SMP system into a VM would be kind of tricky. It'll work because basically you just have to you'll trap the the SMP accesses and stuff like that. But I haven't tried this, and I think there's a whole lot of daemons there that will make it a little tough to play with. And basically the other thing is when you're looking at raw device access, you need to basically write miniature drivers to decode a lot of these device protocols, a TAPI, USB, and things like that. And it's a lot of code to have to write. And so let's talk a little bit about how I can detect this. As the spec said, there's no bit or register or any little flag you can check that'll deterministically tell you that you're running in VMX non-root mode. But there are several things you can do to try and detect that you're running in a VM. Two ideas that I had are, first one, you can try and create a VM. Basic idea is if you're already running a VM, you're not going to be able to create nested VMs and so on. Or you can basically detect instruction latency and basically detect that a VM exit is happening because the instruction is taking much longer to execute than it should. So what I call the VMX test is try and create a simple VM, and basically that just does a random arithmetic calculation. Basically adds two random numbers together, and so you just write out the code, like basically the instruction bytes, to do that, and try and create a VM just to execute those, and then execute a VM call to pass control back to you. If basically the computation was successful and was the expected value, the VM executed. And if it failed, or if for some other reason didn't work, and your processor model should support it, that my MacBook should support this, but it's not. Then something's awry. And I doubted that a rootkit is actually going to fully emulate VMX, but it turns out I was wrong. So you should go see Joanna's talk where she talks about that. So the next approach is detecting VM exit latency. Like I said, some instructions always cause VM exits. And basically, we're just going to use my favorite CPU ID instruction and basically measure the latency that it takes to execute. Because normally, it's a pretty fast instruction. It doesn't really have to do that much work. It has to flush some caches, and then just basically it's hardwired the values in it. And just try to give a benchmark to another slowish instruction. An enter-leave combo when you're running in VMX root, it's about 4 ticks. It's about the same in VMX non-root. Anything that's just shows that when you're running in VMX non-root, you're really running on the bare hardware, and everything is the same speed as native, unless basically the VM needs to handle it. And if we execute this